Good day, ladies and gentlemen. In this lesson, I want to take a look at some of the final skills in our Delta Quarter 3 assignment number 2 package. Specifically, I want to look at the skills that deal with graphing and observing quadratic behaviors and working with linear equations, which you haven't seen in quite some time. Let's get started. If I jump to skill number 18, it's asking you to graph a parabola and state the properties. Specifically, Delta asks you to graph the given equation on the axis that's been given below, and it suggests that you have to plot 5 points, including the roots and the vertex, using the graph, and then ultimately determine the vertex of the parabola. So because this is a nonlinear relationship, immediately you should be thinking that nonlinears are most often graphed from a table of values. I know that because it has an x squared in the actual equation itself. So immediately I'm going to go to my calculator for some help. I'm going to go into my function list, type in the given equation, and I'm going to scroll up and down in my table of values until I get my first y value to be equal to my last. By doing that, I will have centered the vertex. The vertex is happening 2 units time from now when the relationship measures 1. In your workspace to support your work, I would actually only copy down some of the interior points. Obviously, it doesn't make any sense to copy down 2 moments of time ago and 3 moments of time ago because we can't graph as low as negative 15 on the graph that Delta's given us. So we'd only want to copy down from 1 moment of time ago to 5 moments of time from now. That's what I would put as my supporting work. From there, be sure that when you actually graph the work on Delta, that you select the vertex, 2 moments time from now it measures 1, and according to the instructions, you have to have the roots. What's important to remember about the roots of a relationship is that they are when it digs into the ground, so when it measures 0. So we're looking for 1 moment of time ago when the relationship measured 0, as well as 3 moments of time, from now when the relationship measures 0. The 5 points that we want to graph include the vertex, the 2 roots, and any 2 other points you'd like. And it might just be easiest to graph the points prior to the root and after. So maybe you want to do the y-intercept as your 4th point and its symmetrical point as your 5th point. So to actually do this on Delta, I would begin at 0, negative 3, the y-intercept. I would plot that point by clicking on it. I would go to 1, 0, the root that happens 1 moment of time from now, onto my vertex at 2, 1, the symmetrical other root at 3, 0, and then at time 4, it's symmetrical or the same measurement as it was at the y-intercept. 4, negative 3. And as soon as you plot that 5th point, the parabola will show up on its own, and then you just have to state the vertex in the given space. So it will say state vertex, and you'll have to say the vertex happens 2 moments time from now when the relationship measures 1. When Delta describes that process to you in the example questions, they show you an entire table of values. Please don't copy that down. For the second example, if you were going to graph the relationship x squared minus 14x plus 48, I would simply want you to go to your calculator, substitute the relationship into your function list, go to your table of values, and scroll up and down to get your first y value equal to your last, and copy down an appropriate interval of time. And my goal would be for you guys to copy down enough information so that you have the vertex, the center point, as well as the roots, which Delta says you must have, and possibly the 2 points before it. So technically, copying down 5 points would be enough. In some instances, copying down 7 or 9 is appropriate as well. Once you copy down the appropriate points, plot them on Delta appropriately. When you get your 5th point plotted, the parabola will show up on its own. Make sure that you include the roots or x-intercepts as well as the vertex, and you answer whatever question Delta has suggested for you. So for this example question, it says to determine the roots of the equation. So in the drop-down box, you'd have to actually identify 6, 0, or type in 6, 0, as well as 8, 0, when they ask for the properties or the specific details about the relationship. Skill number 19 wants you to compare features of a table versus a graph. And this could be with a quadratic and or possibly a linear. So the very first question says, answer the question below based on the graph of f of x and the table of values for g of x. So the graph of f of x is a parabola, and the table of g of x may be as well, but I'm not sure. It asks specifically in the drop-down box below to compare the y-intercepts of the function. Now, what you have to remember about the y-intercepts is that the y-intercepts are where the relationship crosses the y-axis. It's actually the values at time 0. So the values at time 0 can be identified as 0, some number, or f of 0 equals, because we're putting 0 in place of x, the unit of time. So we want to know what does it measure at time 0. When I look at the graph of f of x, I can identify what it measures at time 0, the y-intercept, by seeing where it crosses the y-axis. And I'll notice that at time 0, it measures 7. F of 0 equals 7. Or another way to say that is 0, 7. If I look for that same information in the table of g of x, the second relationship, I'm simply going to be looking to see when or what the relationship measures at time 0, which is at the bottom of the table. At time 0, g of 0, the relationship measures 8. And based on that information, I can fill in the drop-down box below. The y-intercept of f of x was 7, the y-intercept for g of x was 8, and therefore f of x has a lower y-intercept than g of x. They could have asked about the x-intercept. The x-intercept would have been where it crosses the x-axis. The x-axis or the x-intercepts are also known as the roots, the zeros, or the solutions because they tell us the value of x when the relationship measures 0. So you do have to be a little bit careful to make sure you're paying close attention to the difference between the x and or y intercepts. The very next question in delta, as shown in the example problem for comparing a table versus a graph, says based on the linear relationship of f of x, compare it to the linear relationship of g of x in the table. And in this instance, they do want to know about the x-intercept. What's important to know about the x-intercept is it's where a relationship crosses the x-axis. It's also known as the roots or the zeros. And for the graph, I can identify the x-intercept of the linear relationship as happening 3 units of time ago. So I could say that f of -3 equals 0. 3 units of time ago, the relationship measured 0, because the x-intercept is the time when the relationship measures 0. Knowing that, I could look at the table of values as delta suggests, and I could see that the relationship for g of x measures 0 1 moment of time ago. F of -1, the relationship measured 1 unit of time ago, was 0. And another way of saying that is 1 moment of time ago, the relationship measured 0. And then a drop-down box will come and have you compare them. And you'd have to know that f of x has a lesser or lower x-intercept than g of x. For the next skill, graphing quadratic and linear systems, system means more than one, and because we're talking about a quadratic and a linear, we're going to have two separate relationships here. We're going to have a quadratic, a parabola, and a linear straight line on the same graph, and the solution to a system is going to be where they intersect. In order to graph these relationships, they're going to be giving you each of them algebraically. And it's important to understand that when you work with the quadratic, the x-squared relationship, nonlinears are most often graphed from a table of values. So you'll have to go to your function list, you'll have to type the relationship in, you'll then have to go off to your table and scroll up and down until you get your first y value to be equal to your last. That will center your vertex, and it will get you symmetrical at the same points and allow you to graph this appropriately. Then, with the second relationship, your linear, it's going to be important to rewrite the relationship in your supporting work and identify the slope and y-intercept. Y equals mx plus b. M is the amount that we're repeatedly adding over and over again. In this case, we're adding -2, so this is actually a decreasing relationship. It's going to be going down 2 and over 1, down 2 and over 1. And the relationship at time 0 measures 4. So we're starting at 4, and we're subtracting 2 over and over again. Some people like to prefer to see this relationship as y equals start at 4 and subtract 2 over and over again x number of times. So the linear is kind of easy to graph. In order to graph the linear, you'd start at 4, and you'd go down 2 and over 1, and immediately delta would put a line into that relationship. The quadratic could be a little trickier because you're going to have to drag the relationship throughout the graph. So delta is going to give you a parabola, and in order for you to put it in the appropriate position, and you can see based on what I have on my calculator screen, the appropriate relationship is going to have us take the vertex and shift the relationship to the right 2 units of time, because the vertex is happening 2 units of time from now to measure amount of 3, up 3, and then you're going to have to grab that little blue dot, and the little blue dot is going to allow you to reflect the relationship over the x-axis. So as you pull this little blue dot down, the vertex will stay in place, and you'll see the parabola swing downward. You'll have to make sure you do that accurately, and a good idea would be possibly to check the y-intercept and make sure at time 0 it measures -1, or a similar point to make sure that when this reflects over, you have the appropriate relationship. Delta shows this work, and they don't give you a lot of information as to how to do it. So here's a second example, and in the second example, you'd have to take the quadratic, substitute it into your calculator's function list. You might want to check out the graph to see what it's supposed to look like, but you should definitely investigate the table of values and have some of that detail down as your supporting work. I'd probably copy from 4 units of time ago to 2 units of time from now in a little t-chart. It wouldn't take very long to do. I would just do x comma y, -4, -3, -2, -1, 0, 1, 2. And then I would copy down the appropriate y, corresponding y values. Remember that in order to graph the parabola, delta is going to start you with the parent function, the most basic quadratic you could have, and you're going to be responsible to shift it in the appropriate space. To graph the linear, you'll have to take the relationship and identify the slope and y-intercept, y equals mx plus b, and graph appropriately. This has a y-intercept of 3. You'd start at 0, 3, and the slope is 1 over 1. You go up 1 and over 1. Again, delta doesn't give you a whole lot of detail there in the examples. You may need to watch a video if you're still struggling with that. I did forget to mention a moment ago that the solution to the system are where they intersect, and you'd have to identify those points appropriately to finish the question. So it would be important to make sure that that's done. In the next skill, writing an equation of a linear pattern from 2 points, you have to go back to September and remember that in a linear relationship, we most often use the formula y equals mx plus b. Y equals mx plus b, slope-intercept form of formula, is the most popular form of formula that we have. In this formula, m is the rate of change. It identifies the change in measured amounts over the change in time, and it's the difference in y values over the difference in x's. B is the beginning amount, and it's the value of the relationship at time 0. Whenever we're given two data points throughout time to compare to write a linear relationship, we typically begin by finding the rate of change. In order to do that, you need your slope formula. Change in y would change in x. I would take the 2 points that I'm given in delta, and I would make a quick t-chart. It doesn't take too long to do it all. All you have to do is write x and y, substitute in the first point, -6, 5, and substitute in the second point, -4, -6. And you can see that I did that over here in purple. I then labeled the points x1, y1, and x2, y2, meaning the first time we observed it in the first measured amount, as well as the second time we observed it in the second measured amount. I substituted my y values, -6 and -5, into the numerator appropriately using parentheses, and I did the same for my x values in the denominator. Now, there's some students that would say, Tooch, as soon as you set up a table of values, couldn't you just suggest that the measured amounts are going down 1, from -5 down to -6, and the units of time are going up 2, and I can't, we through just simple observation, write the slope as -1/2, rather than having to compute it, and that's possible. Once you find the slope, the rate of change, you then must substitute that back into your slope formula along with one of the 2 points. Doesn't matter which one you use. I often use the first point because the values are just easier and I don't get confused, along with the rate of change. So in order to solve for the beginning amount b, we need to substitute in for y, m, and x. I chose the first point where the measured amount was -5. That was my y value. You just determined that the slope was -1/2, and the measured amount of -5 was a result of happening 6 units of time ago, so I substitute that in place of x. -1/2 of -6 is 3, and I solve for b appropriately and determine that the relationship started 8 units of time ago. At time 0, the relationship measures -8. That's the y-intercept, the value times 0. Having that information, along with the slope, I can rewrite my equation of my line as y equals -1/2 x minus 8. Substituting in appropriately for the slope, the rate of change is going down 1/2 every unit of time, or down 1 and over 2, and it's starting at -8. It's a really good idea to take that information and substitute it into your function list and check that your table of values has the same matching data points that the question began with. So check that 6 moments of time ago it does measure -5, as well as 4 moments of time ago it measures -6. If those 2 points occur in your table, then you know that you did it correctly. Delta shows this, and the details are a little bit different. In their example problems, they do give you the 2 points to begin with. They show you that you should begin with the slope, but they do not remind you that you're working off of slope-intercept form, so it might be a little confusing as to why you're getting the slope right away. But they do show you that you should begin by getting the slope. They don't begin by labeling the points x1, y1, and x2, y2. Those are those organizational steps that I say are so important for you to remember how to do the question. They also don't substitute using parentheses, which drives me crazy a little bit. You should do that. But they ultimately do get the slope correctly. They suggest that once you get the slope correctly, you should substitute that into slope-intercept form along with one of the points. They do choose the first point as well, and solve for b appropriately. So that is a similarly styled question. Skill number 22, finding the equation of a line from a table, is almost identical to what we just did. Because in order to find the equation of a linear pattern from a function table, it's real simple. You can treat it exactly as finding the equation of a line from 2 points. You just have to focus your attention on the first 2 points, or any 2 points for that matter, but I usually pick the first 2. I label the first data point x1, y1, meaning my first observed measured amount at my first observed time, and x2, y2, the second time I observed it, and the second measured amount. For your supporting work, it's a good idea just to make a quick little t-chart and take those 2 points and put them on your actual workspace. So when you write down the quick t-chart, -2, -9, and 3, 1, I would label those points x1, y1, x2, y2 appropriately. Since I'm working with a linear pattern, I would immediately write y equals mx plus b. 2 most important variables are m and b. I would solve for the slope, the rate of change, right away. There are students who would suggest, Tooch, once you made your table of values, your quick little t-chart, couldn't you just suggest that when you go from -9 up to +1, that's a difference of 10? And when you go from 2 moments of time ago to 3 moments of time from now, it's a difference of 5? And couldn't we just say that the rate of change is an increase of 10 in 5 units of time? And you could. But it's preferred that you're able to use the slope formula and substitute y2, which is 1, in position 1 in the numerator. Substitute y1, which is -9, in position 2 of the numerator, substitute using parentheses, and do the same thing for the units of time. Simplify appropriately, and you should get a rate of change of an increase of 10 every 5 units of time, which simplifies to just 2. Once you find 2, like the questions before where we were solving from 2 points for a linear pattern, you must then go ahead and solve for b. So we just found m. Now we need to find b, the beginning amount. To solve for b, you're going to need to substitute in for y, m, and x. I choose to get x and y from the first point that I was given to work with. So I'm going to substitute in that 2 moments of time ago, the relationship measured -9. I put -9 in place of y and -2 in place of x, along with the rate of change of 2 that we just computed. I then solve a 1.5 step equation appropriately, and I find out that the relationship started at a measured amount of -5. Now, I actually messed this up because -9 plus 4 should be -5. I got +5. And when I wrote my equation as y equals 2x plus 5, and I checked it in my table of values, I noticed that the table looked very different than what Delta had given me to work with. So I knew I made a mistake. And I went back and I looked carefully, and I saw that it should have been b equals -5, and it should have been y equals 2x minus 5. And then when I substituted that into my function list, I did actually get the same table that Data had. I saw that 2 moments time ago, that Delta had. The relationship measured -9. 3 moments time from now, the relationship should measure 1. 8 moments time from now, it should measure 11. So I caught my mistake. And that's a very useful tool to check your work within your function list and table of values. There are 2 more skills, and they're not that bad. Number 23 is comparing linear features from an equation versus a table or graph. And we saw something similar a bit ago with some of our quadratic work. So you just have to be a little bit careful how you read the questions, because the first question I give you an example for says find the slope of each line and compare them. So line A is a linear equation. I know it's linear because the title says so, but also because it's x to the first. And I know that linears I prefer to see as y equals mx plus b. So I chose to solve for y by subtracting x from both expressions, dividing by 3. And then I was able to see that y equals -2 minus 1/3 x, or if you prefer, you could use the commutative property to write -1/3 x minus 2. That way you know the slope is -1/3. This relationship is going down 1 every 3 units time. For line B, I had to use the slope formula that we saw in the past 2 questions. I made a quick little t-chart of the first 2 points, and I labeled the points x1, y1, x2, y2, and substituted appropriately to determine that the rate of change was 2. When you make a quick little t-chart, you may prefer to say 2. I'm able to see that the measured amounts are going up 2, and that's happening in 1 unit at a time, and therefore I want to write my rate of change as 2 over 1, change in y or change in x, and that's acceptable as well. There would be a drop-down box now that would have you make a comparison of those 2 slopes, and you'd say the slope of line A is -1/3. You'd say the slope of line B is +2, and you'd say, therefore, the slope of line A is less than the slope of line B. When Delta gives you an example of these style of questions, the first question that they asked about was the x-intercepts. And to determine the x-intercepts, you have to remember that that is where a relationship crosses the x-axis. Now, what's important about where a relationship crosses the x-axis is that's when the relationship measures 0. That's when the y value is 0. So the x-intercepts are some unit of time, comma 0. I took what's called point slope form of this linear relationship, and I chose to put it in slope intercept form, which is a lot more work than you might have to do. But once I got it as y equals mx plus b, I substituted 0 in place of the measured amount, and I solved for x. And I was able to determine that this equation would measure 0 3 units of time from now. Now, if you understand that the x-intercept is when the relationship measures 0, when the y value is 0, you can immediately just put 0 in place of y and solve the equation in the presentation that was given to you, and you'll also get that x is 3. The x-intercept is the value of the relationship when it measures 0, when y equals 0. So you have to substitute that either into the presentation or into slope intercept form. For line B, when you're actually observing the graph, it's real simple. Just find out where observe it equals 0, and you'll see that happens 4 units of time from now. So the x-intercept of line B was greater than the x-intercept of line A. Or Delta wanted you to suggest that line A has a lesser x-intercept than line B. And then lastly, guys, you're asked to solve linear systems graphically, and system means more than one, and we just saw this with quadratic linear, so this should be familiar to you. And what's important about this particular skill is that you're going to have to identify M and B appropriately. So for the system I was given, the very first linear pattern is in slope-intercept form. I just need to show that the slope is -2 over 1, and that this relationship at time 0 measures -6. For delta, I would be required to go to 0, -6 and plot my y-intercept, and then follow the appropriate rate of change, which would have me decrease 2 measured amounts 1 unit at a time, and immediately delta would put a line in as soon as I got that second point. So a line would come across my page appropriately. For the second relationship, we have a linear pattern. I know it's linear because it's x to the first, first-degree polynomial, but it is not in slope-intercept form. So I might choose to solve for y. In solving for y, I'd subtract x from both expressions, divide by -2 appropriately, and I'd get y equals -1 plus 1/2 x. Y equals mx plus b. My slope is positive 1/2, and my y-intercept is -1. So I'm able to start at 0, -1 and go up 1 and over 2. And with delta, as soon as you plot those 2 points, the line's going to appear immediately. And you just have to remember, as I had forgotten in the similar skill a moment ago, that we're looking for the solution to the system. And the solution to the system is where they intersect. My plotting is a tiny bit off here, but I suspect that they intersected 3 moments of time ago when they both measured -2, and that would be the solution to the system. And those are some of the skills that involve graphing and interpreting quadratic and linear behaviors.